sleep and sleep disorder. And of course, to discuss this topic, we have to also to introduce the basic of EEG, which is such an integral part of any sleep study. This is actually a picture of it's a real picture. It's a class. I think it's in China. So please don't complain that my lecture are boring. I never saw something like that in here. A little snoring here and there, but not that much. Why it's so important? This is really horrible, guys. Horrible not just for the teacher that will question his or her ability, but also for the health. We need to sleep at least 7.5 hours per each night. There are tons of studies, tons of epidemiological studies that were done really in major medical centers that show the negative effect of sleep deprivation. Look at this list. Type 2 diabetes, heart disease. This is actually especially important actually for because as you will see, sleep deprivation is very common in patients that have already other risk factor. So heart disease is really a major issue. Of course, obesity, highway accident. There is they calculate the number of deaths per year, and it's not surprising that it's linked to sleep deprivation. Headache, especially migraine. As I told you, sleep deprivation is one of the most important triggers for migraine attack. Joint problem, this is actually, it was less obvious, but has been replicated in many studies. Also, bone and joint health is going to be affected negatively. And also, this is probably the most important issue, actually. Also, this was replicated in a few studies, but there is a high mortality, especially in women. So you see, this is really, those are big killer, all of them. So imagine how relevant is sleep for our health and wellness. So which kind of animal are you? I think that pretty much we are around the giraffe zone, probably. 4.5, maybe 5. On good night, 5.5. So it's really, and this is very bad, guys, because it's not enough. And but just to tell you that there are absolutely, of course, huge difference. You have koala bear that spend all day sleeping pretty much, but so there is an evolutionary aspect of sleep, and this is very important, guys. When you have change during the evolution, usually it means that that specific function tends to get way more refined. And now we know that sleep has a very crucial and important function in humans. So the normal sleep requirement is not the same for everybody. Of course, a newborn tends to sleep like koala bear, and as I told you, an adult around 7 hours, 7.5 hours is good, but there is an interesting thing that you have to consider. In old age, there is a physiological tendency to sleep less. So you will see clinically lots of older patients, geriatric patients, that they will complain about not sleeping enough, but because they compare that phase to the good old years in which they used to sleep 8 hours, 9 hours, and everything, but already 5 hours in a patient 60 years old or older, it's physiologic. So certainly we have actually some change. So what's the best animal? If you can choose an animal, I suggest you to behave like a dolphin. Dolphins are amazing animals, but they have actually one peculiar characteristic that we still don't know how to explain. They always sleep with half brain, and they always awake with the other half brain. We have a specific pattern, EEG pattern, related to sleep and awakening, and that's what happened in dolphin. It's really absolutely impressive, this thing. So you have this kind of brain wave here that are reminiscent of sleep, and these other here that you see that right now you all have this pattern right here. So it's really something that we can explain. Why do we sleep? We have a theory. We don't know why we sleep. Um, some theories say, but we know one thing, that if we don't sleep, there is a deterioration of the body. So, based on that, some scientists formulated the theory that probably during sleep you are going to regenerate some molecule that you use during your day. Just think of the neurotransmitter, ATP, protein synthesis, hormones, and so on. There is also another evolutionary theory. As you know, during the evolution, each system tends to save energy. So this is a saving energy system. There is an hedonistic theory. We sleep because it's so good and make us feel very, very good. But the most important thing that it's actually now, it's the super hot topic in neuroscience, guys, especially also for Alzheimer, is that sleep is important for learning and memory, specifically for memory consolidation. As you know, when you have, we discussed that last week, when you learn something, the process starts, of course, with the learning phase, then you have short-term memory, long-term memory, and then sometimes we have to retrieve those old memories. But in this process, there is a crucial phase. The memory need to be consolidated. Otherwise, they will not be transformed in long-term memory. So memory consolidation that has some specific biochemical and neurotransmitter and so on that modulate this effect take place during sleep. So we have a different form of learning that take place in different sleep phase. Another important issue, guys, we discussed about long-term potentiation and long-term depletion, synaptic plasticity last week. So this is basically how we upgrade our memory in our computer. So with learning and experience, we are able to upgrade or downgrade some circuit. This is a crucial, those are the basis for learning and memory. Some form of plasticity take place during sleep. So there are specific form of plasticity that take place in there. Based on this finding, now there are very innovative, actually. There's a lot of innovation and technology on this field, specific in new treatment in patients with Alzheimer or memory loss that take place during sleep. So as you know, we can stimulate the brain with current, magnetic field, many other technology, and it's possible to do actually this thing also during sleep. There have been studies, several, like 4 or 5 studies, so it was replicated. If you induce stimulation, if you stimulate in specific sleep phase, you enhance long-term potentiation. So in theory, you can enhance memory in this way. Based on this finding, now we have some clinical trial in patients with Alzheimer with this stimulation in specific sleep phase. This is linked, of course, to this new concept about memory and synaptic plasticity in sleep. So we have a circadian rhythm, and we are not the only one. As you know, basically all the mammals, they have a circadian rhythm. In some mammals, those circadian rhythm lasts several months. Just think at migration, birds, and so on. In our case, we have just a 12-hour kind of cycle that is related to the light. So we are awake when light is on, and we sleep when light is off. So we have some 24-hour cycle. So we need some sort of biological clock or pacemaker, if you want, to dictate this rhythm, to switch from awakening to sleep and the other way around. We will have many areas in our brain that you all know, that we mentioned already. They're mostly in the brainstem, that function in this way. Some area will promote alertness, and some other area will promote sleep. So it's a balance. When you go to sleep in the evening, the sleep promoting structure take over, and the other way around in the morning. Light is extremely important, guys. And so, as you know, if you, I don't know if you noticed this pattern. I'm sure that you did. If you read in the evening and you leave the light on, you have some trouble in getting to sleep, especially the induction of sleep can be difficult. So the light cycle is extremely important. As you know, we detect photons with the retina. So how do you detect in the evening this decrease in light that will trigger our sleep? We have a specific pathway from the retina all the way up to a nucleus in the hypothalamus, which is called suprachiasmatic nucleus. As you know, hypothalamus is a collection of nuclei. Those nuclei control bodily function, some of them blood pressure, water intake, body temperature, and so on. This specific nucleus receives input from this pathway. Those are fibers in the optic nerve that will not follow the usual pathway leading to occipital cortex. There is a shortcut to hypothalamus, and the message is there is a drop in light. The suprachiasmatic nucleus will send input to a gland that you already know where it's located, this pineal gland. Remember this gland that is located in the posterior portion of the diencephalon, and this gland will secrete melatonin. Melatonin will function in this way as a sleep inductor. Okay, so you have a cycle. So from the suprachiasmatic nucleus, pineal gland, secretion of melatonin, increase in sleep. And everything starts with this drop in light. Okay, so remember, suprachiasmatic nucleus is one of many regions that will control the sleep induction, and also, of course, the pineal gland. As you know, melatonin is, you can find melatonin over the counter. And it is a quite good sleeping aid without a major side effect. But in order to be effective, you need to follow the physiologic secretion of melatonin. So if you take melatonin capsule 2-3 hours before bedtime, there's a good chance that you will promote sleep. If you take 10 minutes before going to sleep, it's not going to work. That's a common mistake because there is a time, this is the physiologic, so you have, the drop in light. Let's say, just think what happened around 7 o'clock, 8 o'clock, drop in light, and then at 11 you start to sleep. So this 2-3 hour pattern, it's the physiologic, and of course with individual variation, it depends on where you live and so on, but that's the usual pattern. So if you mimic this pattern, they are actually highly effective. Now we have another generation of drug that they are agonists of melatonin receptor, and they work actually quite well. Those are to be considered specifically in an older patient. If you have older patient with the complaint of insomnia and so on, you certainly cannot prescribe benzodiazepine because, as you know, GABAergic drug enhance confusion. And there is also, they give trouble with balance, so that you increase the risk of fall. So among many other options, melatonin, it doesn't work on everybody, but it's certainly worth to try. And so already we discussed about 2 key regions. Remember that this pathway from the retina to the suprachiasmatic nucleus releases glutamate. It's a glutamatergic pathway. Okay. So again, those are axons of the ganglionic cell. You remember the ganglionic cell, the axon of the ganglionic cell form the optic nerve. So those are special fibers inside the optic nerve that are not linked to vision. Their function is to detect light. So you remember that in retina we have a photoreceptor. There is a special kind of photoreceptor for detecting light, and the pigment in there it's called melanopsin. You remember that we have the opsin, conopsin, rhodopsin. Those are the one for vision. The one to detect light is called melanopsin. Just remember melatonin, melanopsin. Okay. So suprachiasmatic nucleus and pineal gland. But we have a clear pattern when we are awake and we are asleep. Something changes in our brain. We can detect those changes with an EEG. As you know, we do EEG routinely to make a diagnosis of epilepsy and many other conditions, but also is an integral part of sleep study. What is EEG? We detect with special sensor the electrical activity of our brain. But so far we discussed about structure with and neurons. So we always talked about action potential. If you consider a single neuron, the electrical activity of a single neuron is an action potential. But we have billions and billions of neurons in our brain. And imagine a complex function such as memory. We still don't know how many structures are important for memory. Hippocampus, cortex, prefrontal cortex, temporal lobe, and everything. So you have communication and connection among different lobes in our brain. How do they communicate? They have to share some sort of common rhythm. So we call those electric rhythm oscillation. Okay, so if I have activity in frontal lobe that is connected with my parietal lobe, it means that they will have an electrical activity which is similar, synchronous it's called. So that's what we collect and detect with the EEG. We detect those oscillations that come from electrical activity of billion and billion of neurons. Imagine like, an orchestra director, and then you have the orchestra. So the orchestra director gives specific indication, and every solist play a specific sound that will give an harmonic sound at the end. In our brain, we have several areas that function as an orchestra director. They dictate the rhythm. They are located in many, many places. The most important one are in thalamus. So neuron from thalamus send input to cortex, and in this way they can change the electrical activity of cortex. We have a pattern typical of awakening, pattern typical of sleep, and there are also some other patterns typical that you find in patient in a coma, which is a condition that is somehow in between. All those are variant of consciousness. So we define consciousness, our ability to switch to this different state. So you can be awake, fully attentive, less attentive, you can be asleep, a patient can be in a coma, you can do meditation, so your brain goes also while you are still awake, you have pattern typical of sleep, and so on. So we are able to change our consciousness, but sometimes disease change that, such as brain trauma and so on. Coma is a pathological case. Why we have those orchestra director? Because we have a spatial ion channel. Okay, so if I tell you rhythm, it means frequency. So I can have a frequency of 10 hertz. All the solists play that sound at that frequency, 15, 30, and so on. So orchestra director, but physiologically, what is an orchestra director? It's a special ion channel with function as a pacemaker. It closes and opening according to that specific rhythm. So beside the ion channel that I discussed so far, you have some other, we don't need to go in detail. They are called T channels, but not only, we have several of them that they function as a pacemaker. They open and close involuntarily. without action potential and everything, because their job, like the one that you have for the cardiac conduction and so on, and the cardiac rhythm. Also in the brain, we have a specific, also in that case, they are channeled. So how we detect this oscillation? We put electrode on our scalp, and each electrode will detect the electrical activity from a bunch of neurons that are close by. Clinically, we use 20 electrodes, but as I told you, it depends. For research, we can go much higher because we can be very sophisticated. I just did it actually in the morning before coming here, an experiment, and we used an EEG that has 250 channels. So just to tell you how complex and laborious is the analysis in those cases. But that's for research. For clinical purpose, 20 channels. Where do we put those channels? There is a system. It's called International 1020 system. We take some metric because each one has a head of different shape. So we take some measurement and we position those electrodes in a consistent way across the subject. Then you have wires that are connected to an amplifier, and the amplifier basically you change it. You are able on an oscilloscope to see the signal with a rhythm. That's what is EEG. Okay, so electrode, bunch of neurons close by. What we record come from the activity of all the action potential of those neurons. It's very organized, so we have a bunch of rhythm, but we don't have many. We have several of them, but not so many. That's how they look like. So right now you are listening at what I'm telling you, so you are very attentive to the slides, to what I'm telling you. If I do an EEG on you, the preponderant rhythm that I'm going to find is beta rhythm. The frequency is about 14 Hz or above that. That's the pattern that you find when you are awake and attentive. Then my lecture becomes super boring as usual, so you switch to a less attentive state, but you're still awake. In this case, you are resting, but you are still awake, and this rhythm is alpha rhythm. The frequency is between 8 and 13 Hz. After a while, my lecture becomes super boring. So you switch to the other phase in which reminiscent of sleep. So the rhythm becomes much slower, prevalent theta rhythm, 4-7 Hz. You have this rhythm in some form of sleep. And then if you are really bored, you will sleep. And in this case, you will have a super slow rhythm below 4 Hz that are typical of deep sleep. Those are delta rhythm. Okay, so beta rhythm, alpha, theta, and delta. Okay, that's what we get clinically with the thing. And remember, they come from the activity of billion neurons that are localized around those electrodes. That's the physiologic thing. You might have a patient with epilepsy. In that case, you will see that the electrical activity can become really high, and everything depends upon which kind of epileptic seizure you have. You can see here that fast rhythm and then when it gets very slow, look here, bigger amplitude but slower frequency. Remember, frequency is number of cycles per second. So how many stages we have in during sleep? So let's say you go to sleep, it takes a while, and then you start to sleep. We have different stages. We have 5 different stages, and then that form a cycle, and after that we repeat the cycle again. You cannot switch from one step to another one. So you go from stage 1, 2, 3, 4, and then there is a special stage 5, and then you repeat the cycle several times during the night. An entire cycle lasts about 1.5 hours. So we repeat at least 4 or 5 of those cycles during a night. So first stage, You start to sleep, but if you hear, a loud sound and everything, you can awake very easy. So it's a very superficial sleep. In this case, you are awake and relaxed, basically. So you will have the rhythm of awakening, quote unquote, which is preponderant alpha rhythm. Okay? And again, this is that phase that is in between being awake and be in a deep sleep. Then you switch to stage 2. You will still have alpha rhythm, but in between you have some other rhythm and some other factor that you see on an EEG that are peculiar of this phase. You will have so-called K complex and spindles. Look at this guy here. This is a spindle, and this is a K complex. So a combination of spindle and K complex suggests stage 2. Again, when we do a sleep study, we can record this. So you look at the EEG, you see spindle and K complex, you know that that's stage 2. If you see mostly alpha, stage 1. Then we move to the next stage, 3. Stage 3 is getting into the deep sleep phase, so the rhythm becomes slower. The slower the rhythm, the deep is the sleep. So you will have mostly theta rhythm, and you see you might still have a combination in some of those. You might still see some K complex and so on, but the preponderant rhythm is theta. It's getting slower, and then you go to the deepest form of sleep, which is stage 4, in which, as you see, the rhythm it's very, very slow. It's below 4 hertz, and that's the deepest form of sleep. It's the most restoring. Okay, so if you have a sleepless night, but you have somebody wake you up, but you have enough duration of stage 4 sleep, you will wake up in the morning not tired, because stage 4 it's the most restorative. It's also super important, this stage 4, because memory consolidation take place in this phase. Okay, so when you say sleep deprivation, I have insomnia and sleep deprivation, the effect on your body and performance, it depends upon which part of night you wake up, how long it takes to wake up, how much the duration of each different phase. And especially, stage 3 and 4 are deep one. After this, you have a special stage. Stage 5, we call that REM, rapid eye movement. You know everything about eye movement, and again, I'm very proud of you. We did that part in great detail, and as you will see next week, it will come very handy to understand all those stroke syndrome in the brainstem, because you have a combination of paralysis and ocular abnormalities. But so you know everything about saccades and fast ocular movement. In this phase, rapid eye movement. So if you observe a patient, a subject in this phase, you will see that this subject move the eyes very, very fast. Okay, so don't get scared. If you see someone with those, this is perfectly physiologic. Those are very fast saccades that take place during REM. That's why it's called rapid eye movement. And remember, the superior colliculus was crucial in development saccade, and there's a lot of activity in the superior colliculus during REM. That's why you have this eye movement. But it's not the only special thing that takes place in this phase. If you do an EEG, you will find alpha rhythm. So you are asleep, but your brain functions like if you are awake, because alpha rhythm is typical of awakening. Another thing, you know about muscle tone. We discussed it a lot, linked to stretch reflex, abnormality in cerebellar disorder and everything and so on. If you check muscle tone during REM, it's almost abolished. It's called REM paralysis. There's no any resistance. You may see several patients that tell you, doctor, I think that I got a stroke last night. I woke up and then I almost fell. I didn't have any strength. It took a while to get back. I think that it was like a TIA of a stroke. It's not.